Okay, good afternoon. Is that right? Welcome to this talk. I'm Chris Lynas. I'm an aerospace engineer by background, and I thought it would be interesting, certainly for me, to take you through this talk about what it turns out that I didn't know about aerodynamics and advisability of prime numbers, quite a lot of stuff about 3D printing and my printer in particular, quite a lot of frustration and something that would probably be described as ultimately fairly pointless. This is something where I like to describe it as the world's most pointless desk fan. You can see it over there on the chair. It's a fairly small thing for what caused me quite a lot of problems. It's roughly a timeline that I'm going to show you. It's illustrated by an approximately chronological order of some tweets that I sent, because these have got a bunch of photos that I put forward. This is really at the beginning, and this is October 2014 when I really started it, where I was, as you can see, enthusiastically voiding the warranty on a desk fan. This really is the bit that underlines the pointlessness of this whole exercise, because I wanted a desk fan, but I started with a desk fan. It took me till January 2015 before I actually had any actual hardware to print. They were very, very big prints, and as you can see there, I started with a desk fan, but it was boring, so I wanted a much better one. This was the problem, this was the statement, this is the thing that started me off. I thought, as an aerospace engineer, it would be really nice to have a fan that looks like a jet engine. So I initially had to say, well, what type of jet engine? If you look at something like this, what you're seeing is the axial flow jet engines that pretty much every aircraft in the world will have these days. It's rare you'll see one that's any other type. It's axial flow because that central rotational axis is the direction that the flow's going in. It's a series of fan blades. So to begin with, I wanted one that looked like that, and it doesn't really work. Unfortunately, as you could see, the motor that I had, because I wanted a fan motor, I wanted something nice and quiet, it was just too big. And the outer diameter is very much constrained by my print bed, which is fairly small. It's a mini Kossel. It's only about 170 odd millimeters that you can get away with. And I just couldn't get any flow past it. So I changed my mind and I went to a radial flow jet engine. There's a few photos here. These are all fairly old. This is a cutaway of one that tells you the type of thing you can see. And the bit that you should be looking at is the bit at the front, the bit with the big blades on. This is the impeller. It's a centrifugal compressor. These are some of the earliest types of jet engine. It's the type of one that Sir Frank Whittle first put together when he first started making jet engines. It wasn't the same architecture as the very first jet engine to fly, which was in Germany. That was an axial flow jet engine, but the first ones over here were radial flow centrifugal compressors. And it looked quite nice. I thought that might be quite good, and I thought I could make a jet engine style fan that looked a bit like that. There were other types. That was a single-sided compressor. You got double-sided compressors. I did think about doing these, but in the end I decided not to. I decided to go with the single-sided one. And although this isn't from a jet engine, I think it's from a diesel boat, I just thought that looked really nice, so I modeled it on something like that. Broadly, what this compressor is doing is absorbing some shaft power from the engine. In the normal jet engine way, that's a turbine at the back that's in the flow that you've heated up through the compressors and through the combustors. It takes some of that energy from the flow and pipes it through that compressor to give you an increase in pressure. Initially, though, it's increasing the speed. My compressor is only powered by a very, very small fan, so the pressure rise is pretty negligible. It's more like a centrifugal fan, but that means a lot of the adaptive features that I've got really aren't suitable, but it would work, I hoped. The nice thing about these is that they can give you a very big pressure rise over one stage. The reason they were used in early jet engines is because they didn't want to have a whole bunch of components. They can be quite cheap. They're quite wide, which meant that the engines tend to be fairly wide. But in terms of efficiency, they can be quite good. What's actually happening is that the blades around the eye at the center, they're grabbing hold of the flow. There's a bit at the front called the inducer that just starts to pull the flow down into these blades. Those then fling it out. And at the tip, you can expect it's going to be nearly following the speed of the tips, just about, with some outflow. So it's spiraling out from the compressor. This is giving you then something that in my design looks a bit like that. I had some full height blades, I had some half height blades. I eyeballed pretty much everything in this by eye, assuming that my intuition as an engineer would guide me, which in some cases was very much not the case. I did the blades in OpenSCAD. In fact, the whole thing is done in OpenSCAD and Inkscape. The blades were done by some kind of deep magic that I really honestly still don't understand. Basically, what we see is the compressor is acting as the contraction here, which in subsonic flow is going to speed the flow up. Then you have to have the diffuser, which is going to decrease the speed and increase the pressure. That's Bernoulli's principle. This is true in subsonic flow. In supersonic flow, it's very much not the same thing. Supersonic flow, if you accelerate it to Mach 1 at the contraction, you're going to be seeing that it will accelerate in the diffuser and it will be work very different way. This is what the layout is. You can see the fan in the center and the diffuser. It can be vaned, it can be vaneless, but in my case it was vaneless initially, and then I put some vanes in, but mainly for structural reasons. This is what it looks like. The motor goes in the center inside that housing. The inlet is a bell mouth. There's an annular outlet, which is where it comes around the outside of the motor, and the vanes are there to pass through the cables and also to hold the parts together. However, as you can see, a sense of dread was very much beginning to build for me at this stage. I was eyeballing this. I thought that my intuition would take me through. I am very much not an engineer who works on jet engines. I do use them, but I don't design them. And all the way through, I was finding that there was stuff I didn't know. I learned a lot about these motors as well. These are shaded pole induction motors. They're used in pretty much all fans. If your fan, your desk fan, is noisy and rattly, it's because your power is really bad quality. And it's probably a note that you should talk to your electricity provider, which I didn't know. The way they're working is there's a coil of metal which is creating an oscillating magnetic flux. The oscillating magnetic flux is going to be giving you a certain amount of movement. The movement backwards and forwards won't necessarily cause the rotor in between, in the round space, to move in any one particular direction, which is a bit of a shortcoming for a fan where you need to know what way it's going to go. So the shading, these copper pipes, those are going to give you something that will cause a bit of a delay of the magnetic flux, which creates a preferred direction. These are really, really nice for fans because they're really, really quiet. There's no commutator noise. There's not going to be any rattling or scraping. But it does mean they're very, very weak, which is a bit of an issue for that fan, but broadly not as bad as it would have been for the original fan. So I decided to keep going with that, even though I discovered that there were some issues with it later on. This is the motor housing, 6.5 hour print, which at the time is one of the biggest that I'd done until I printed one of the next parts, which was even bigger. I mounted the motor in there. It pretty much fits. I used the time immemorial tire knot in it, method of strain relief. And then this is the impeller that I designed, and it all worked reasonably well. It fitted, it ran without the fairing. At this point, everything seemed to be pretty good. It was after that point where I'd actually built stuff that I actually decided it might be a good idea to actually look at some books. This one was one that proved to be helpful in telling me a bunch of things that I probably should have realized to begin with. And then I moved on to the fan shroud. This is really the biggest print I'd ever done. And it really was only just printable on that machine. You can see how big this is. It's filling the whole of the build plate. However, when I say it's printable, I think that's possibly a little bit debatable. On the side near the display at the front, it flattened it because it decided, no, I'm not going to let you use that space because I think it's too wide. And also I had to take the bed probe retraction tower off because it was going to clash in it, and I only realized that halfway through the print. So this was a bad idea, but 8 hours. Again, that was the biggest print I've ever done. And it was finished, and it worked. It produced airflow. It didn't look that pretty, but I was pretty pleased with it at the time. And I thought, that's really good. Did you count the number of blades that I put on when I showed you those pictures? Because unfortunately I didn't. It worked, but the noise was just intolerable. One of the things which I kind of knew, but which I'd completely forgotten about, or rather assumed would not be relevant, was I had 12 blades and 6 stators. And I knew that that would probably make some noise. And I thought, it's a low power fan, how bad can it be? The problem was, turns out, really bad. What's happening, and hopefully the video is showing, is this. Every single time one of the blades passes one of the stators, it produces a little pulse of noise. And it happens 12 times every rotation, and it all happens at 6 places at the same time. I thought it wouldn't be bad, but this is a really, really, really efficient way of producing noise. This is an air raid siren. In fact, for this first version, I estimate it was significantly more efficient at producing noise than it was at producing airflow. Something better, which is what I moved through to, was this. This is changing one fan blade, so I have 11, and one stator, which is now 5. This is a really, really minimal change, but you can see it's not all happening at the same time. You're getting fewer every rotation. The difference in noise was absolutely huge. I mean, really, really huge. Way more than you could hear, which means it's way more than 3 decibels, which would be a doubling in the amount of noise energy. My first version was this. My second version, and not even a very good one, my second version was significantly better. So I thought, yep, that's brilliant. I redesign, I reprint, got some filament anxiety along the way as I was getting extremely close to the end of a reel. Version 2 was much better. I was doing a drawing machine in parallel. It was all going very well. It was much, much quieter. I was feeling really, really happy. This is the one that you can see there with a few modifications. However, one of the problems I had was that there was a funny grinding noise that happened most of the way through a print. And what I found was happening was that the noise on the previous version was so utterly horrible. I mean, you couldn't be near it. The noise was so horribly whiny that I never really had it switched on for more than about 30 seconds. And it turns out that the glass transition of PLA, which is what I was printing with, is way, way below the temperature that a not very efficient shaded pole motor reaches when you put it in an entirely sealed box, which is what I'd done. What that meant was I needed a significant amount more cooling. So I redesigned it, and I took this as an opportunity to get a few more little aerospace features in it. What I did was to use NACA ducts. NACA ducts are one of these things that you frequently see being put onto things in films and TV programs to try to make it look more aerospacey. And the aerospaciness of it is usually spoiled by the fact that many people put them the wrong way round. A NACA duct is a really fabulous thing. As a brief aside, on the left-hand side there, you can see a YF-93, which was one of the first jet-engined fighter aircraft that the US built. And they put NACA duct intakes on it because they're extremely low drag. NACA is the National Advisory Committee on Aeronautics, I think. It's the predecessor of NASA. These were really, really low drag, and they liked putting them on aircraft because they thought low drag is good. It'll go faster. The problem is that while it does go faster, in theory, in practice, it doesn't. Because although it's low drag, you don't really get a lot of pressure off it. The one on the right-hand side is what they changed it to when they realized that, because with the jet engine, it's all about pressure recovery in the duct. When the flow comes in, you slow it down. When you slow it down, the pressure increases. And the more that pressure can increase, the better and happier the jet engine will be, and the more thrust you'll get. And so the problem with this was that while they were gaining on the drag, they were losing a huge amount on the thrust, which meant that, unfortunately, they didn't last very long. But also, all this told, especially now, as aircraft are starting to get a lot more electronics on board, a lot of electrics, you'll see NACA ducts all over aircraft. This is the original paper, I think it's back in the 30s. This is the original paper where they described the specification. You know what? I'm just going to hold this. This thing's, for those who haven't been noticing, this thing's been gradually sinking throughout the whole talk. What you've got here is the original specification. It's the drawings that they did of their experiments in the wind tunnel in order to work out how to do these. I just thought that was good. This was version 2.1, and that is what you see in front of you here. It was assembled, and it was running. I had 2 NACA ducts on the top. I had 2 NACA ducts on the bottom. If anybody wants to have a look at it, you're welcome to do so. I might even be able to plug it in, although I guarantee you will be underwhelmed. I wanted to see if anything melts, and it did. I put a little thermistor through the vents at the back, and the motor was well over 70 degrees. The problem is, as with the previous one, I mean, don't get me wrong, this one will run for about half an hour before something starts to melt. The other one would run for about 10 minutes before something starts to melt. The problem is, basically, the motor really just isn't that efficient, which is not a problem for its application. It's not designed to be efficient. It's designed to be really long wearing. It's designed to be nice and quiet. That, unfortunately, inefficiency means that energy is going somewhere, and unfortunately it means it's going into heat. What that means is I'd actually have to have some kind of standoff, because at the moment that motor is bolted directly into the PLA structure, which is pretty good at conducting heat into it. So, as some conclusions, I made a desk fan. It wasn't very good. In pretty much every measurable way, this was worse than the one that I started with 2 years ago. So it took me 2 years to get a really bad desk fan, but it was boring. That's what I'm holding. This one is more interesting. I learned that there were a lot of things that I'd completely forgotten about turbo machinery. I learned that my engineer's intuition is probably not as good as I think it is when it comes to things that aren't really my field. And there were quite a lot of things that I actually never knew about turbo machinery, and some other things which I found out, which I hope I've managed to tell you when you also think they're interesting. However, my one thing that I hold, it did look a bit like a jet engine. If you wish to make one, please don't. If you wish to make one, or make it better, which, believe me, please do, and then tell me so I don't have to do it. All of the files are open. There's a GitHub which you can see. I can pass you some details if you wish. So on Thingiverse, if that's your type of thing. Basically, you'd probably have to get a motor the same as mine. I'm thinking about making one with a slightly nicer brushless DC motor, but fundamentally, it works in a sort of, well, for suitably small values of work. So that's the end of the talk. Thank you very much for your time. There's maybe no more than 2 or 3 minutes for questions. To be honest, it probably might be better is if you just catch me outside. Does anybody have anything they'd really want to ask now? Good. Okay. I'll be down here if anybody wants you. Thank you. Thank you very much.